Hello there, it's Miss Willett, just here to talk you through acids and alkalis and what happens when we mix them together in particular. Looking at first strong acids, followed by weak acids and what buffers are. So as promised, the first thing we need to think about is what happens when you mix a strong acid with a strong base. Now in this case, you've got to think about what is in excess, what is your limiting reagent, and then you've got to use whatever you've got in excess of to figure out how you're going to find the final pH if that's what you're aiming for. If you've got an excess of acid, then you can just slot that straight into minus log H plus to get pH. If you've got excess hydroxide, you need to add the extra step of using Kw to find out the H plus concentration and then plug that into the pH calculation. So let's have a look at some worked examples because they make everything better. And in the first worked example, we're going to use an excess of H+, but we don't know that yet. We've got to do the maths to work it out. As always in chemistry, it's really important to lay out your calculations really clearly so we can see what's going on. And to do that in these sorts of calculations, I use two different things. The first thing is to structure everything around an equation. In this case, because I've got a strong acid and a strong base, I use OH minus plus H plus goes to make H2O. The water's obviously going to be a massive excess, so I can ignore that, but I need to figure out my amount of OH minus and H plus. I also use ICE, but in this case, E stands for end rather than equilibrium. And then we need to work in concentrations, which is also really important. So I also try to remember square brackets at the bottom of my structure. Now my initial moles of hydroxide and hydrogen ions are found out from just doing N equals CV. Moles is concentration times volume, obviously converting volume into decimeters, and taking into account the fact that we've got sulfuric acid, H2SO4, which is dibasic. It releases 2 H plus ions, obviously unless we're told otherwise. That means initially that I've got 0.00375 moles of OH minus and 0.01 moles of H plus. So my H plus is in excess and my OH minus is a limiting reagent in this case. And that means I'm going to remove 0.00375 moles of each of those reagents so that all of the OH minus is used up, and I'm left with 0.00625 moles of H plus. And then I've got to divide that by the total volume of 75 centimetres cubed, so 0.075 decimeters, to get a concentration of 0.08 moles per decimeter of H plus. And then I can slot that into my pH. Minus log 10 of 0.08 is a pH of 1.08 to 2 decimal places. But what about if I have an excess of OH minus? Well, the starting point is still the same because I might not know for sure that I have that. So first I've got to work out what is my limiting reagent, what is an excess, and I've got to do that using exactly the same structure. So in terms of moles of reagent here, it's still N equals CV to work it out. And I end up with 0.02 moles of OH minus and 0.0125 moles of H plus. Now this time my OH minus is in excess, so I'm going to use up all the H plus to end up with no H plus left at the end. And 0.0075 moles of OH minus. So I divide that by the total volume, which in this case is 125 centimetres cubed, or 0.125 decimeters, and that gets me a concentration of 0.06. But I need to do an extra step because that's OH minus. So I need to slot it into my Kw expression to get my moles into a concentration of H plus and then slot that into my pH. So I need to know my expression for Kw and what the value of Kw is at room temperature and pressure. So my expression is H plus times by OH minus, and that's equal to 1 times 10 to the minus 14 at room temperature and pressure. But I've got to rearrange that to get H plus from OH minus. So my H plus is going to equal 1 times 10 to the minus 14 divided by my OH minus concentration, which is at 0.06 that I've just worked out. That gets me a H plus concentration of 1 times 0.67 times 10 to the minus 13. And therefore my pH is minus log 10 of that, which is 12.78 to 2 decimal places. And it's always worth sense checking. It's an alkali that makes sense as an answer. Now the next thing we're going to think about is what happens about weak acids. And actually, weak acids can form these really interesting solutions called buffers that are really, really useful in all sorts of things in everyday life. And a buffer is a solution that can resist pH change upon addition of small amounts of acid and alkali. And lots of human biology includes buffers. Buffers are really important for things like COVID tests. You probably remember squeezing out little bits of buffer into that lovely swab that you've just written the back of your throat with whenever you do a COVID test. Really, really useful because lots of biological things need to stay at a specific pH, and buffers can help us to do that. Now, buffers are made from weak acids, and they have to have both HA and A minus there in large enough quantities so the HA will react with any hydroxide, releasing more H plus ions so that you can use up all that hydroxide and maintain a similar pH, not identical, but similar. And it's the same for H plus. If you add small amounts of acid, that will react with A minus, forming more HA, and again the pH will stabilise. It will be relatively close to the original pH value of the solution you've just added it to. Now, there's lots of ways we can form buffers, and one way is by mixing an excess of weak acid with a strong base, such as sodium hydroxide. Now, the structure of these calculations, if you're finding the pH, is pretty similar to what we've done before, but this time, rather than using H+, because my weak acid doesn't fully dissociate, I'm going to use HA in the equation. So, similar structure, but this time we've got HA and OH minus, and we're forming A minus, and that A minus, again, is going to be pretty important because that's going to be part of my Ka expression later. So in this case, using N equals CV, I've found out that I've got 0.025 moles of my weak acid HA, and I've got 0.015 moles of my OH minus. And that's again really important. So what that tells me is that I've got an excess of HA. So my OH minus is all going to get used up. 0.015 moles of my HA is going to get used up reacting with the OH minus. And I'm going to make 0.015 moles of A minus. So these are amounts of moles at the end, so I now need to find the concentration. And I'm going to do that by dividing it by the total volume, 125 centimetres cubed, or 0.125 decimeters. And that gets me 0.08 moles per decimetre cubed of HA, and 0.12 moles per decimetre cubed of A minus. So I now need to slot that into my Ka expression. Remembering Ka is equal to H plus times A minus all over HA. And I'm going to need to rearrange that to get H plus. So I leave H plus on the side it is, and I switch over and move HA onto the side with K. And A minus onto the side by dividing it. So I slot in the values I have. pKa needs turning back into Ka by doing 10 to the minus 4.76. And then my concentrations I've just worked out, so 0.08 on the top and 0.12 on the bottom. And that gets me a H plus concentration of 1.5 times 10 to minus 5, which gets me a pH of 4.94. Which makes sense for something that's got a fair chunk of weak acid in it. It's not too high, but it's still below 7. Now, the question I've posed to you is this solution a buffer? And the answer is yes. Yes, it's a buffer, and that's because it contains both HA in the form of CH3COOH, ethanoic acid, and it also contains A minus, CH3COO minus. So both HA and A minus are present. Now, sometimes I can make these calculations extra easy for myself by half neutralising the acid. And the way I'd know this has happened is that I've got exactly the same concentration of HA and A minus, like in this example here. So I'd start out life with the same structure, but in this case, once I work out my moles of HA, I figure out very quickly it's 0.02, and my moles of OH minus is 0.01. And that means I'd be left at the end with 0.01 moles of HA, no moles of OH minus, and 0.01 moles of A minus. So these two are the same. And that means that in my Ka expression, my HA and A minus would cancel each other out, because if you divide a number by itself, you get 1. And therefore, pH equals pKa, so pH is equal to the 4.76 I've been given. These buffers are also really effective because you've got the same amount of HA as A minus, which means they're equally as good at resisting pH changes caused by acid and pH changes caused by alkali. And yes, this is a buffer because it contains both HA and A minus in significant quantities. Now I can also make a buffer by just mixing my HA, my weak acid, with its conjugate base in a salt form. So for example, here I've got sodium ethanoate. The ethanoate ion is the conjugate base of ethanoic acid. So once I mix the two together, I get significant amounts of HA and A minus. And I'm going to use a slightly different structure to work this out, but still keeping my answer very structured. So I've got a set of steps to follow and it's really clear what I've done. Now this time I'm just going to use the dissociation of my weak acids, and also I don't need to think about pH. Well, I need to think about pH changes. I don't need to think about concentration changes. Nothing's reacting here. I'm just mixing things together. And very handily, I've already been given the concentration of my weak acid. I know it's 0.01. So no calculation is needed here using the volume. But I will need that in a minute for my A minus. So sodium ethanoate is NaCH3COO minus. So what I've done is I've swapped the H plus from my ethanoic acid for a sodium ion. And I know it's a single sodium ion because sodium has a 1 plus charge. And then what I've got to do is I've got to use moles equals mass divided by RFM. So my 2.05 divided by my RFM of sodium ethanoate, which gets me 0.025 moles. But that is just a number of moles. I need to turn it into a concentration. I'm going to do that by dividing it by 0.5, which will get me 0.05 moles per decimeter cubed. Then I'm going to slot that into my Ka expression to get H+. I can use my pre-rearranged one if I've learned it, or I can rearrange it again from scratch. So H+ is equal to Ka times by Ha all over A minus. So Ka is my 1.74 times 10 to the minus 5 times by my 0.01 all over 0.05. And so my H+ is equal to 3.48 times 10 to the minus 6, and my pH is equal to 5.46. And once again, this solution is still a buffer because I've got significant amounts of Ha and A minus in the same solution. So in summary, the way you find out the pH of a buffer depends really on how you've made it. So if you've made a buffer by mixing Ha and A minus, you need to find the concentration of Ha and A minus in your solution, slot those values into your Ka expression, rearrange to find H+, and then find the pH. If you find a buffer or make a buffer by mixing OH minus with an excess of weak acid, then what you need to do is you need to find out the moles of HA that are left over, slot into Ka, and then find my H+, and then find the pH. Whereas if you half neutralise your weak acid, you've made your life easy for yourself, because not only have you made a really good buffer, you also can just then find pKa, and that is your pH of that buffer solution. If you have any questions, do feel free to drop me a message. And thanks for watching.